Let's take a look at Sankey diagrams and energy density. So a Sankey diagram is supposed to be a convenient way to show energy transfers in a device or process. It's just a graphical representation of energy transfers or energy flow in a device or a process. So I'll show you an example. Here is a light bulb, like an old classic incandescent light bulb. If we put 100 joules into one of these light bulbs, we get 10 joules of light energy out, and 90 joules is lost as heat or thermal energy. So a Sankey diagram would look like this. Over here on the left, you see 100 joules was the energy supplied to the light bulb that went into the light bulb. And then here we have an arrow that represents the useful stuff coming out, this 10 joules of light energy. That's what a light bulb is used for, is to produce light energy. So that's the useful stuff. And then the lost energy is over here. It's this curved arrow right there. And notice, the arrow size is proportional to the amount of energy. So this 10 joules is quite a bit smaller than the 90 joules right here. And in fact, in a perfect Sankey diagram, they should be exactly proportional. So the 10 joules should be 1 unit wide, and the 90 joules should be 9 units wide. And then the one over here that's 100 joules, that would be 10 units wide. All right, let's take a look at another one. Let's say we have a kettle that's heating some water for us. And let's say that we supply 200 kilojoules of energy to the kettle, and 160 kilojoules goes into heating the water, and then 40 kilojoules is lost to the surroundings. So the Sankey diagram for that would look something like this. We can calculate the efficiency pretty easily with a Sankey diagram. The efficiency here would be the useful energy that came out divided by the total energy that went in. So here 160 kilojoules divided by 200 kilojoules, which is 80%. Now, another term that we're going to see thrown around a lot is degraded energy. The degraded energy is this energy that's lost. So it's the energy that you put in, but it doesn't do anything useful. So in the case of the light bulb, that was the 90 joules that was lost as thermal energy. And for this kettle, that's the 40 kilojoules that was not going into heating up the water. Sankey diagrams are not just used for energy, they can be also used for power. And they can also be used in very different ways. I've seen people use Sankey diagrams to reflect job searches. So the arrow on the left could reflect all of the job inquiries you put out. And then the different arrows that come out of that could represent, say, the number of interviews you got versus the number of rejections, and so on and so on. Energy density is another concept that we'll look at. The energy density is a description of fuel that's used in a process. So it is the energy per cubic meter, or energy per volume, that a fuel can provide. So for example, let's say we're thinking about coal. Coal has an energy density of about 5 times 10 to the 10 joules per cubic meter. That means each cubic meter of coal provides about 5 times 10 to the 10 joules of energy. And of course, different fuels would have different energy densities. Gasoline has approximately 3.5 times 10 to the 10 joules per cubic meter. So if you had a cubic meter of gasoline, it's quite a lot of gasoline, but if you had a cubic meter of it, it could provide 3.5 times 10 to the 10 joules of energy. Natural gas is about 3.6 times 10 to the 7 joules per cubic meter. And uranium, when it's used as nuclear fuel in a nuclear power plant, can provide about 1.3 times 10 to the 18 joules per cubic meter.